On January 29, 2022, the Sun unleashed a relatively minor solar flare from a particularly active spot on its surface. 49 satellites lifted off the Florida coast on a February afternoon in 2022. Within days, most of them were gone. Not stolen, not sabotaged, just pulled out of the sky by a fairly ordinary disturbance in Earth's own magnetic field, one that had been forecast in general terms days earlier, though nobody predicted it would cause this much damage. A handful of the falling satellites put on an unplanned show over the Caribbean, streaking and breaking apart in the pre-dawn sky above Puerto Rico. Some witnesses on the ground genuinely mistook it for a meteor shower. It wasn't. It was a small fortune in orbital hardware, tens of millions of dollars, coming down all at once. To this day, it remains the single largest loss SpaceX's Starlink program has ever experienced in one event. Yet the thing responsible for it all had never been considered a serious threat. A few days earlier, the Sun released a solar flare on January 29, 2022, classified M1.1, from an active region designated AR12936. Attached to it was a coronal mass ejection, a burst of solar material heading toward Earth. NOAA's Space Weather Prediction Center picked it up almost immediately, and within a couple of days issued its forecast. A minor geomagnetic storm, nothing that stood out as unusual. Scientists would eventually classify it as G1 to G2 on NOAA's 5-level storm scale. Minor to moderate, the kind of geomagnetic activity that occurs roughly 1,700 times over the course of an average 11-year solar cycle. Weather scientists referred to this as quite a common situation in terms of geomagnetic activity. In other words, routine. What the pre-launch numbers didn't fully capture was how a storm like that would behave at one very specific altitude. The atmospheric models used to plan the mission were built on density assumptions that, as later analysis would show, underestimated just how much even a modest storm could thicken the atmosphere barely 200 kilometers up. That gap wouldn't become obvious until it was already too late to matter. So the launch went ahead as scheduled. A Falcon 9 rocket lifted off from Pad 39A at Kennedy Space Center in Cape Canaveral, Florida on February 3, 2022, carrying the Starlink Group 4-7 mission. 49 Starlink satellites released from the rocket in 2 stacks, one of 24 and one of 25. This was SpaceX's standard approach. Satellites go first into a very low parking orbit, only around 210 kilometers up, before their own onboard krypton ion thrusters gradually raise them toward their real operational altitude, roughly 550 kilometers up. That low starting point is worth noting because it's a deliberate safety choice, not an oversight. If something is wrong with a satellite at that stage, the thin edge of Earth's atmosphere pulls it back down and burns it up quickly, rather than letting it linger up there as debris for years. Under normal conditions, that's exactly what should have happened next. A steady climb toward their final orbit and 49 new additions to the constellation. The thing is that the conditions weren't normal. The geomagnetic storm from that January flare reached its most disruptive phase right around February 4th, a day after launch. It heated the thermosphere, the upper layer of Earth's atmosphere, and caused it to expand outward, directly into the altitude band where the freshly deployed satellites were sitting. Atmospheric drag on the satellites spiked, by SpaceX's own account, by as much as 50% compared to previous launches. Ground teams responded the way they'd been trained to. They turned the satellites so their thin edge faced forward, like a knife blade cutting into the wind, rather than presenting their broad side to the oncoming atmosphere. It's a sound maneuver. The problem was that it also meant the satellites couldn't fire their thrusters and climb while sitting in that position, and the thickened atmosphere wasn't going anywhere soon. Over the following days, most of the 49 lost more altitude than they could recover. One by one, they dropped low enough that the atmosphere took over completely. The most visible moment came in the very early hours of February 7th, when observers with the Sociedad de Astronomía del Caribe, an astronomy group based in Puerto Rico, caught it on camera. two separate bursts of light breaking apart across the sky, about a minute apart from each other. Analysts who reviewed the footage afterward couldn't immediately agree on whether that was one object breaking into two pieces or two separate satellites re-entering close together. Ground radar operators, including the US Space Force and the tracking firm Leo Labs, worked in parallel to keep tabs on what remained of the fleet as it came down. SpaceX confirmed the loss publicly on February 8th, attributing it to the storm and estimating that up to 40 of the 49 satellites would re-enter the atmosphere, or already had. That number, up to 40, is the one that made headlines that week, and it's probably the number most people still associate with this event. But that wasn't quite the final figure. Once the data was fully reviewed, independent researchers confirmed the real count: 38. 11 of the original 49 made it through and successfully raised themselves into their intended orbit. 38 satellites burned up completely, at an altitude low enough that not a single fragment reached the ground. No injuries, no debris field, just a very expensive lesson in how much force an otherwise unremarkable storm can carry, if it hits at exactly the wrong altitude, at exactly the wrong time. Most retellings of this story stop at one line: a solar storm knocked out some Starlink satellites. That's true. It's just not the whole picture, and the scientists who kept studying this event for years afterward found something more complicated underneath it. The first confirmation, published by NOAA and its research partner CIRES in November of 2022, backed up SpaceX's own explanation. The storm heated the atmosphere, that increased drag, and that's what brought the satellites down. For a moment, it looked like the case was closed, except researchers kept digging. A follow-up study in 2023 made a point worth mentioning. This had only been a minor storm, not a strong one, and it still managed to cause the largest single loss in Starlink's history. That combination, an ordinary storm with an extraordinary result, is what kept scientists returning to this event long after the headlines had moved on. In 2024, a research team out of IISER Kolkata, working alongside a space physicist at NASA's Goddard Space Flight Center, went further still. Their conclusion: the storm alone doesn't fully explain what happened. It took three things at once: the modest solar event itself, SpaceX's decision to insert the satellites at such an unusually low altitude, and the satellites' own physical shape, which made them unusually vulnerable to drag in the first place. Remove any one of those three factors, and this story might have ended very differently. One detail that's worth paying attention to: a 2025 study went back through the tracking data and found that of the 38 satellites lost, 32 were never tracked at all by NORAD's space surveillance radar before they re-entered. They came down too fast and too unpredictably to even be caught by systems built specifically for this. The researchers behind that study went so far as to say that no published explanation, even by 2025, fully accounts for how that many satellites could disappear that quickly. So if you've only ever heard this story summarized as "a solar storm took out some satellites," that's the headline. It's not the complete science. Years later, part of the mechanism behind one of the most closely studied incidents in modern satellite operations is still, technically, an open question. It's worth asking at this point what actually changed because of it. Quite a lot, and quickly, as it turns out. SpaceX's very next Starlink launch, less than 3 weeks later, used a meaningfully higher and less elliptical parking orbit and carried fewer satellites at once. The company also updated its satellite's flight software specifically to handle this kind of space weather event going forward, and began exploring an independent tracking beacon to give ground controllers a clearer picture of where each satellite actually is. By that summer, in a formal filing, SpaceX put the confirmed number on the record: 38 satellites re-entered and lost to the atmosphere. The forecasting side changed too. NOAA and SpaceX began a formal data-sharing partnership, and by the middle of the following year, NOAA had rolled out an upgraded atmospheric forecasting model. It was a direct response to what this event had exposed, that even routine, forecasted space weather could behave in ways the existing models hadn't fully anticipated at very low altitude. None of this slowed Starlink down. The constellation kept growing. Newer satellite generations launched in the years that followed, deploying from different orbital profiles, shaped in part by what was learned here. Today, the constellation numbers more than 10,000 satellites, up from around 2,000 at the time of this incident. And in all that growth, nothing has come close to matching this single loss. It remains to date the largest one-time loss in Starlink's history. The financial side was never fully settled, at least not publicly. SpaceX has never confirmed an official cost. Independent estimates put the value of the lost hardware alone somewhere between $10 and $20 million. And once you factor in the cost of the launch itself, some estimates run as high as $100 million. As University of Southampton space debris researcher Dr. Hugh Lewis put it, that higher figure only makes sense if you include the cost of the launch. SpaceX never confirmed a number either way and simply absorbed it. Beyond the dollars, this event became part of a larger, ongoing conversation. SpaceX and its supporters point to exactly what happened here as evidence their safety design works. No debris field, no risk to anyone on the ground. Satellites that failed exactly the way they were built to fail, by disappearing completely and quickly. At the same time, it sharpened existing concerns from astronomers and space sustainability researchers about how crowded low Earth orbit is becoming and about a separate, slower-moving question: what happens to the upper atmosphere once thousands of satellites eventually burn up in it? Independent researchers have found that satellite re-entries release aluminum oxide into the upper atmosphere, and that in 2022 alone, re-entries of all kinds pushed the total amount of atmospheric aluminum up by roughly 30% above natural levels. Scientists describe the long-term atmospheric effects of this as still poorly understood, and some have even petitioned the FCC for closer environmental review of mega-constellations as they continue to grow. Both of those things, the debris safety success and the atmospheric question mark, are true at the same time. Neither one cancels out the other. What I find most remarkable about this event is more than any single number, is the gap between how ordinary it started out and how much attention it's still getting. More than 4 years later, this remains one of the most closely studied single events in the modern satellite era. Not really because of how many satellites were lost, but because of how much a fairly ordinary, forecasted storm was able to do to a brand new batch of satellites all at once, before they'd even had the chance to reach safety at their intended altitude. And because scientists are, even now, still working out exactly why. Thanks for watching. Leave a like and subscribe.